All right, it's time to go ahead and get started today. First of all, before I forget, and I'll repeat myself once more people get here, we have quite a few people not here today. But over on the sideboard over there, sometime before you leave, write down, who your partner is for the assignments. Because remember, like I mentioned last time, for the software and hardware assignments, you work as a two-person team, but you just make one submission for each team. All right, so I just want to know like who you're going to be partners with. So, and please write last names. Because there are some people, I think I have at least a few people with the same first name, maybe not in this section, but maybe with my other sections. All right, so today, the lecture should be a lot shorter than what it was last time. So you'll have time today in class to work on the assignments. And I already talked about the first assignment that's due tomorrow. That's the first software assignment that's in the lab manual. And remember, you're just doing part 2. Okay, we did part 1 in class. So just like I said last time, and this is true for all the software assignments, there's 3 things you turn in, the flow charts, test cases, and then the code. And out of those 3, probably the one that gives people the most to think about are the test cases, okay? Now, it's something you graded on, so, I'm not going to tell you specifically what the test cases are because, it's one of the difference between this class and 133, at least the way I teach it, right? 133, I used to give you the test cases, but in this class, you got to figure them out. But generally speaking, of course, you want to make sure the test cases show that your program is, functioning the way it should. Like here, you want to make sure that you give it a negative 2's complement, it's going to give you the right positive 2's complement and, vice versa. But then you also want to test like fringe cases, like you might want to test 0, right? And you want to test like the minimum value and the maximum value and any type of fringe cases you can think of. Dr. Hummel, I sat in on one of his classes one time, and he would always tell his students, no matter what they were coming up for test cases for, whether it was a software program or a piece of hardware, is try to break it. Like give it test cases where you're trying to break it. Okay, so that's generally what you're trying to do. And you'll get better at it as the quarter goes on. So I mean, like this first assignment, if you miss a test case, I wouldn't worry too much about it. As long as maybe that's why people are it's stuck. Sorry about that. Didn't mean to laugh. I was wondering where everybody was. Okay, let me just mark it down here. So Ava's here. Avery. Daniel. And are you Christian? Yeah. Hey, Jack. They did Evan come in? And Michael, I saw Michael. See who else? Timmy? So Timmy didn't come in. Chad? He's not here.
Got here
Okay. Chris?
yet.
Okay. Oh, how about Alexander? And Chase? No Chase. Okay, so I got everybody that was locked out. Sorry about that. Okay, so yeah, people that just came in, over on the sideboard, just sometime before you leave today, if you would tell me who your partner is going to be for the assignments. Okay, because remember we're doing 2-person teams. Everybody does their own work, but then you only submit one per team. And I was just talking about the first assignment that's due tomorrow. Again, the 3 things you turn in: flow chart, test cases, and code. And I just said a couple of things about the test cases. Just, you want to make sure that your test cases are showing that the program's doing what it's supposed to do. So again, in this case, remember, whatever the input is, you want to change the sign. And since it's 2's complement, how do you change the sign of a 2's complement number? Yeah, you take the 2's complement, right? You invert it and add 1. So, you definitely want to have a couple of test cases that show, it takes a positive 2's complement, makes it negative, and vice versa. And then you want to do like fringe cases, minimum value, maximum value, 0 would be a good one. And anything else you can think, because again, in your mind, you should be thinking anytime you come up with test cases, whether it's for a program for the software assignments, or whether it's test cases for the hardware assignments, always, be thinking, you're trying to break it, okay? All right, so as you can see up on the board, today, there's a little bit I want to review from CP 133, but not as much as last time. And then and I want to review a little bit of what we went over last time that had to deal with this class. And then there'll be some new material for CP 233, where we talk about how you program the otter, okay? Because you're going to see the way we program the otter is different than, say, how you program an Arduino, okay? All right, so first of all, from CP 133, you learned about active high and active low input. So who can tell me what that means? What does it mean when you have an active high input? What does it mean when you have an active low input? No, it doesn't have to do with that. I think what you're thinking more is about synchronous and asynchronous, which we're going to get to next. But just if you say that an input is active high, what does that mean?
Oh,
Yeah, exactly. It just means that when you make that input a 1, whatever that input is, like if it's a reset input, it's going to reset, right? And if it's active low, it takes a 0 to make that input happen. So active high, it takes a 1. Active low, it takes a 0. Now, in this class, all the inputs of the otter, they're all active high. Okay, so you'll see when you start building the otter, all the resets are active high, all the loads are active high. Okay, so everything for your otter is active high. Okay, now we get to asynchronous and synchronous. You learned about those two types of inputs also in 133. Who can tell me the difference between synchronous and asynchronous?
Synchronous depends on the clock. Asynchronous can just ignore the clock.
Exactly. You're exactly right. Yeah, synchronous depends on the clock. In asynchronous, the clock doesn't matter. Now, even though a lot of times people, know the definition of the two, and by definition they know the difference, they still sometimes have difficulty seeing the difference between the two, like say on a timing diagram with waveforms. So just to kind of drive this home, I want to go through this example here and show you the difference between a synchronous input, like a synchronous reset, and an async. Now, before I show this, one other thing here is, do you remember how in 133, sometimes you had a sequential circuit like a flip-flop that was RET? What does that stand for, RET? Rising edge trigger. And sometimes you'd have falling edge trigger. Can someone tell me the difference between those two? Like, what's the difference between rising edge trigger and falling edge trigger? Okay. Exactly. That rising edge is the transition from 0 to 1, right? At the time of that 0 to 1 transition, that's what we're talking about. And then falling edge is just the opposite, right? The time of this 1 to 0 transition. So in this example, let's say, we have rising edge. That's why on the clock signal here, I put little arrows on the 0 to 1 transition, right? Because that's what we look at when we have a rising edge. So if we had an async, if we had an asynchronous reset that's active high, So you can see here, here's our reset signal, well, here's our clock, like we said. Here's our reset, it starts at 0, and you see right at this time here is when it transitions 0 to 1. And here's our output is initially a 1. Also, you may recall from 133 that what we mean by reset is that when that input is active, the output's gonna go to 0, right? So if this is an asynchronous, right, asynchronous active high reset, when is this output gonna go to 0? Starts off at 1. And then at this time here, that's when the active high asynchronous reset goes to 1. So when would this output go to 0? In other words, when does the reset happen? This here, you're saying?
Yeah.
That's actually what would happen with synchronous though. Right? See, this is async. Remember, async doesn't have anything to do with the clock, right? You don't even have to consider the clock if it's asynchronous. So since it's asynchronous, instead of happening here, because that's what would happen when it's synchronous. See, if it's asynchronous, the minute reset becomes active, the minute in this case it goes to a 1, that's when it would go to a 0. So right at this time, if it's asynchronous, it's going to go to 0. Okay, but if it's synchronous, right? So if it's synchronous, then like, is it Ivan?
Yeah.
Then, like Ivan said, it would stay high until this edge of the clock here. Then it would go low. This example shows the difference between synchronous and asynchronous. See, synchronous, once that synchronous input becomes active, it's going to happen. Synchronous, it's not enough for the input to become active. It has to be active during the time of the appropriate transition of the clock, which in this case is the 0 to 1 transition. So you see, this is when it would reset in the async case. This is where it would reset in the synchronous case. Okay, does that make sense? Now, in this class, your Otter, the CP233 microprocessor that we have, all the inputs are synchronous except for 1. Okay, so you're going to be dealing mostly with synchronous inputs. Okay, there's one exception to that.
So if RFT and the clock both rise at the same time, it's ignore it, right?
Okay, yeah, now you bring up an interesting case. There is a possibility where you can have a synchronous input changing at the same time as the appropriate edge. Like if this 0 to 1 transition happened right here, right at the time the clock was transitioning, that would create an ambiguous situation. That's something you want to avoid, right? Because if the change of the synchronous input is exactly at the time of that clock transition, flip a coin whether it's going to happen or not. Okay, so yeah, that's a good point that, that's something you got to watch out for because that can cause an ambiguous case. Yeah, that's something you definitely don't want to happen anywhere in your microprocessor because, that's when you have situations like that, that's when the microprocessor might work 50% of the time. It's like intermittent, right? Because sometimes it's occurring when it should and other times it isn't. Okay, so that's what I wanted to review from 133. Do you have any questions about that before we move on? We're going to review a little bit of what I talked about last time from this class, but then we'll move on to something new. Well, I mean, I'm only showing one input reset, but if this was part of a flip-flop or something, once you're not resetting, now the output would depend on the D input, what it was doing, or if you had a set input, which when you activate a set input, it makes the output 1, right? Because that is opposite of resets. Okay, so yeah, my purpose here wasn't to show like like a timing diagram of a device, like a flip-flop. It was just to show the difference between synchronous and asynchronous. But yeah, you know, if you had another input, like a D input, eventually, like when that D input goes high at the time of a transition of the clock, then the output would go up. Yeah. Any other questions? Okay, so from last time, we talked about several things that had to do with registers. Okay, now, hopefully, and I probably shouldn't emphasize this last time. Hopefully, you kept this diagram that I gave you last time, the otter diagram. Do you still have that? If you do, you might want to take it out and take a look at it. If you don't have one, maybe someone sitting next to you has one that you can look at. And last time, specifically, we talked a little bit about this module, that's the memory module. And we talked a little bit about one of the modules right to the right of it, the reg file. Now, one of those two has 32 registers. You remember which one of those two has 32 registers? You got a 50-50 shot if you get, yeah, it's the reg file, very good. Yeah, the reg file has 32 registers. And all 32 registers can hold 32 bits. Okay, so there's 32 registers and they all can hold 32 bits. And also last time I kind of mentioned, but you know, you might have, you know, it's easy not to remember if you just hear it one time, so I'll repeat it. All operations occur in the reg file. So what I mean by that, you know, all operations, when you do a not, like for software part 2, you know, what you're going to hand in, you're going to have to do, or at least one way to do that problem is, you know, you'll have a not command, right, to invert all the bits. Well, that inversion of the bits, it's going to happen in a register that's in the reg file. Okay, when you add, like, you know, if you add 1 to something, right, that addition is going to happen in the reg file. Okay, if you do any sort of logical operation, you'll see when you start to look more closely at the instructions in the ISA for the otter, there's instructions where you can AND contents of registers together. You can OR contents of registers together. You can do all kinds of logical operations. They all occur in the reg file. Okay, so all operations occur in this reg file. And again, there's 32 registers and they all can hold 32 bits. Now, since there's 32 registers, and remember last time we talked about how registers have an address, right? Which is just a number that distinguishes that register from all other registers. So if I have 32 registers, how many bits do the addresses have to be? Well, what's the minimum number of bits that I would need? How many?
5.
5, right. How'd you get that? Yeah, very good. Yeah, it goes back to what you talked about in TP 133, that the number of values equals 2 to the number of bits. Right, so if I have 5 address bits, I can address 32 things, right? And as we talked about last time, you know, these reg file registers, we label them X0, X1, X2, all the way through X31. So, you know, X0 has address 0, X1 has address 1, and it's going to be 5 bits each address. All 5 zeros for X1 and X0 has 5 zeros for its address. X1 would have address 00001, right? So on, all the way to address 31, which is 5 ones. Okay. So, you know, when you're writing your software, we use the X0, X1, and so on to identify the register we're using, but hardware-wise, it's known by a 5-bit address. Okay, and then also, as we said last time, the first 5 registers, registers X0 through X4, those are special registers that, you know, we'll learn later on in the quarter why they're special. But for your assignments, don't use X0 through X4 yet. You know, you can use any reg file register from X5 to X31. Okay? Now, we've got the reg file, and then the other block that we talked about last time, right, that has to do with registers is this memory module. Okay, and the memory module also has registers that can hold 32 bits. But the memory module has many, many more registers, right? Because it starts at address 0, and there's 32 address bits for the memory module. So the memory module, each register can hold 32 bits, and each address is 32 bits. So, you know, we start at all zeros and we end up with all Fs. And, you know, you could figure out how many registers that are, right? Because if you took this number and divided it by 4, right? Because remember how we talked about last time that the memory module, it's byte addressable, right? So each register that's 32 bits has 4 bytes, right? Because a byte is 8 bits. So just divide 8 into 32, that's 4. So you see each 32-bit register in the memory module has 4 addresses, right? Because this byte has an address, 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 right? And so on, all the way up. And then also, we talked about last time that the memory module is made out of these segments. Right, we have a code segment, a data segment, a DAC segment, then there's some reserved segments which are not used, and then we have this memory mapped IO segment. Okay. Now, what goes in the code segment? Code, which is going to be your what? Code of what? Instructions, that's your program, right? So when you program the otter, that's where your program is going to be, right? The listing of your instruction. And specifically, the code section is put in the prog ROM. It's put in, you know, ROM stands for read-only memory. So as I mentioned last time, the prog ROM is part of the memory module. Okay, so when you look at this diagram, your program is going to be in that memory module in a specific part of it, this prog ROM. Now, the memory module is more than that. Okay, it's more than the prog ROM. The prog ROM is part of the memory module. It's like embedded, if you will. Okay, and that's where your program is going to be. That's where the assembly language instruction is going to be, right? The 1s and 0s for those assembly language instruction sets. You're going to program the otter with. Okay. Now, another thing about the memory module is these 3 segments right here. Okay, the stack, the data segment, and the code, they're referred to as real memory. And what's meant by real memory in this case is that's the portion of the memory module that's going to reside in the FPGA of your Basis 3 board. Okay, so real memory, these 3 segments, they're actually going to be within the FPGA of your Basis 3. You know, the reserved and MMIO, okay, the reserved and the memory mapped IO, that's outside that FPGA. Okay, so the reason why that's important is because if you just look at these 3 segments that make up real memory, the addresses go from 0 to 000 FFF. So these addresses here are determined by hardware. Okay, see, we couldn't make real memory bigger unless we get a different FPGA, different, developmental board. If we use like an Intel board or, some other manufacturer, it might be different. But this is a limitation of the Basis 3 board. That's all the memory that we can, fit in the FPGA.
So the memory module saying it's like a table of contents for the memory module that you have to the right of that, like kind of like goes for each one.
Well, what I'm showing here is, the byte addressability of the memory module, and that applies to all of this. So, the MMIO is also byte addressable, just like the stack is, just like the data segment is, just like the code is.
But those are one and the same right there.
Right, yeah, this is just showing, the reason I drew this, and I'm gonna talk more about it coming up, but as I mentioned last time, the memory module, its registers are byte addressable, meaning every byte has an address. Now, again, contrast that with the reg file. The reg file is not byte addressable. The reg file is just each register has an address. Okay, yeah, but I'm gonna get more into why I have this up here. Because I want to talk about this in more detail than I did last time, but that's coming up. Okay. So one other point I wanted to make about this is that this range of address from 0 to 000 FFFF, that's set by the FPGA. That's hardware limited. But how the segments are divided up, the programmer decides how to do that. So the fact that the code goes from this address to that address, the programmer decided that. In fact, it was Dr. Hummel. He was one of the designers. Okay, but later on in the quarter, you'll see that you can change this. Okay, by the end of the quarter, you'll see that, I'll show you how you could change it if you wanted to. Okay, so these segment ranges in addresses, those are easily changed by the programmer. But this range of address here, that the programmer can't change, because again, that's set by the FPGA, the limitation of the FPGA that's on the basis board. Okay? And then also MMIO, right? Memory mapped IO. And by the way, we talked about this last time. What's memory mapped IO? What does it mean? Like, where did this address come up last class in the assignment? This 1100, oops, I'm putting at the wrong one. This one here, 11000000. Yeah, that was the switch address. So memory mapped IO is just that input and output devices have addresses, right? That's how the microprocessor distinguishes between input and output devices, is by an address. Okay, the switches have this address. And then the LEDs have address 11000020. If you saw in that first assignment that we did in class. Okay. All right. So the next thing I want to talk about, and this gets to why the memory module is byte addressable. You might be wondering, why is the memory module byte addressable and the reg file isn't? Well, the quick answer is because of how we use them. Because of how we use the reg file, we don't need it to be byte addressable, but because of how we use the memory module, we do need it to be byte addressable. Okay? And what it has to do with is some of the instructions that we have in our instruction set. Okay, we have these load instructions, load word, load half word, load byte. Now, these are the signed ones. There's also, the ones for unsigned that have the U. Okay, and what I'm about to say applies to those as well as these. Then we have store word, store half byte, or store half word and store, byte, okay? Well, there's something called a word boundary that you sometimes have to be, concerned with. What I mean by sometimes is when you're doing a load word or a store word, or you're doing a load half word or store half word. Any of these types of instructions, you have to be wary of crossing a word boundary, because if you do, something good's not gonna happen. Oh, move the camera, thank you. Yeah, I always forget to do that. I appreciate you reminding me, thank you. Let's see, let's just turn it over here. There we go, thank you. Yeah, so anytime you're dealing with a word or you're dealing with a half word, you have to be mindful of not crossing a word boundary. So let me talk about what that is. Okay. Well, as we've said, with the memory module, every byte has an address. So if I go to either load or store a word, the addresses that I can use is I could use any of these addresses over here, because how many bits is a half word? 16. So if I were to use this address 0 for a half word, it's gonna take this data at these 2 bytes. Okay? If I use this address for a half word, it's gonna use these 2 bytes. If I use this address for a half word, it's gonna use these 2 bytes, and that's all okay. But what I can't do is I can't use a load half word or a load or store half word with this address. Because if I use this address, it would try to take this byte and this byte, but that would be crossing a word boundary, because how many bits is a word? 32. So you see, you can't take a byte from one word and another word. It doesn't work. That's what we mean by crossing a word boundary. That's not allowed. See, when you're storing a byte or loading a byte, you don't have to worry about that, right? Because a byte's never going to cross a word boundary because it's only bits. Same sort of thing when you're loading or storing a word, you can't cross a word boundary. So if you're storing or loading a word, you can only use these addresses. You can only use address 0, 4, 8, C, and so on, right? Because if I tried to use address 1 for storing or loading a word, it would take this byte, this byte, this byte, and try to take that byte, but that would be crossing a word boundary, and it's not going to work. Okay, does that make sense? All right, so that's what's meant by you can't cross a word boundary.
So is there anything stopping us from just writing the instruction to access memory at something that's not a word boundary using a word command or a word instruction?
Oh, that's a great question. For the design of this microprocessor with the ISA, it's not possible. But, and this gets to how the software and the hardware is all interrelated, there could be a microprocessor like that, or you could sit down and design one like that if you wanted to. You know, the reason this isn't possible is just because of our design. Yeah, so it's not like this is necessarily true for all microprocessors. There might be a microprocessor out there. I mean, I don't know of one, but there could be one where this is allowed.
What I was asking is more like if we have the instruction in memory and the processor tries to run that instruction, what will happen? Is it just?
Well, actually, that actually gets to my next thing I was going to bring up, because, you know, we just said that words are 32 bits for this microprocessor. Now, if you go and you look at the ISA and you go to look at the instructions for this microprocessor, they're all 32 bits. So all the microprocessor instructions are words. So the addresses for instructions in your program, they're going to be separated by 4, because your first instruction is always at address 0. And then the next instruction is going to be at address 4, and then address 8, and so on. So I mean, does that answer your question or?
I mean, I guess if you try to load something from memory with a instruction that calls for 4 bytes, but you do it on something that's not a word boundary, like if the bits in the instruction are telling it to do that, but it can't physically do that, what will happen?
Well, there's another, I think maybe the answer to your question is something where you're gonna get to next class, and that's what's determining the address of the instruction that we're gonna use is another component, like on this diagram, it's this PC, this program counter. See, that's providing the address to the memory module in order for it to know which instruction to use. And, we'll talk about next time how, we always reset that program counter where it's always accessing instruction 0, the instruction at address 0 first, and then from there, it just increments by 4s. So there's never a case where when you're running a program that it's gonna choose some address other than something that's divisible by 4. Once it starts at 0, then everything's divisible by 4. So I think that it's kind of like what you're going to, yeah. But again, there could be another design, another microprocessor design where the instructions are delineated in some other fashion, but that's how it is in this case, so, yeah. Okay, well, you see, that was one of my questions here that we just answered that. For the Otter, all the instructions are 32 bits. Okay, so your instruction addresses, it always starts at 0, and then they go by 4s, right? Your first instruction's at 0, second instruction at address 4, next instruction at address 8, and so on. Okay? All right, so the next thing to talk about, and I think we got enough time before taking a break, is how the Otter is actually programmed. Like I mentioned at the beginning, we can't program the Otter like an Arduino. Okay, where you just like download the file right to the Otter. The way it's done is that we use the RARs to generate a mem file, and that mem file has a hex listing of your program. Okay, all the instructions in your program are in hex. And then you load that into Vivado. Okay, so it's like another file in Vivado, this .mem file. And when you load it into Vivado, it's the same process as when you create like a design source. Okay, so on Canvas, if my computer went to sleep, I guess. See if that is back on. Oh, maybe I turned it off. I thought I kept it there. I guess I turned it. Slowly but surely. It's not fun getting old, believe me. Stay young, don't get old. Okay? We should be coming on soon, hopefully. Oh, yeah, yeah. Okay, so for your next assignment, because remember, the first assignment, that software assignment, that's due tomorrow. But the next assignment, which is the first hardware assignment, I think I have it listed as Wednesday of next week, but I forgot about that. We don't have class on Tuesday because Monday's a holiday, and then that Tuesday you're following your Monday schedule instead of Tuesday schedule. So I'm gonna change this. Right now on Canvas, it's Wednesday of next week, but I'm gonna change it to Friday of next week. So this assignment, part of it is showing you how to program the Otter, or at least how to come up with the file that you put in Vivado to program it. So one of the things I wanted to point out, first of all, is you're gonna need this design source file here. This is the ProgROM system Verilog file. Dr. Hummel designed this, so you know, we're not expecting you to design the program, it's already designed for you. Okay, so you would just download that into Vivado. And I have a video. Let's see. So if you click on meeting two, the link for meeting two, it takes you to this page here. And I think I mentioned this last time, but let me say it again, that for each meeting, I put my lesson plan, basically what I plan to cover, you know, it's my notes. So, you know, it might be a good idea that when you're listening to me up here, you look at that because that's basically what I'm going to cover. But also in my lesson plan for this meeting, I have this video, and this video steps you through how you use RARs to generate that mem file. And then it also shows you how to load that mem file into Vivado. Okay, and then you're going to use Vivado to, you know, verify some things. So, you know, basically that video is stepping you through a lot of what you need to do for this first hardware assignment. Now, there is a part of this hardware assignment that is outside RARs and outside Vivado that you do first, and that's what I want to talk about next. Okay. Oh, the other thing here is this first hardware assignment, the criteria, you know, what you submit is different than all other hardware assignments. Okay, so like when you go to Canvas, you know, up here I have, you know, this is the criteria for the software that we talked about last time, right? That's the three things that are listed on the board over there. And then you see right here, hardware assignment submission criteria. What's here is for all the hardware except for hardware 1. Okay, and also the final project, which is, you know, something more that we'll talk about later. Okay, so I just want you to know that what you submit for this hardware assignment is different than all other hardware assignments. And I have it up here. Okay, so you would probably want to take a picture of this before you leave. Okay, so the first thing you want to do in this assignment is create a table like table 1 from the assignment page. So if you go to the lab manual, actually, let me show you where the lab manual is in case you didn't see it before. Okay, on Canvas right here, the very top, that's the lab manual. It has all the software and hardware assignments. We're not doing all the assignments in the lab manual. Okay, you know, I think we're doing most of the hardware ones and about half the software ones. Now, don't feel like you're getting cheated because actually some of the software that we're not doing during the quarter is part of the final project at the end. Okay, but anyway, it's just one of the ways I'm trying to make the course a little bit more manageable. So if you go to the lab manual and you go to assignment hardware 1, part of it is this here. Okay. So look at this here. 0, 4, 8, C, 1, 0, 1, 4. What do you think that is? What do you think those are? Those are addresses, and they're addresses of an instruction, because addresses of an instruction are separated by 4 and they start at 0. So you see, this is the first instruction, second instruction, third instruction, so on. Okay. Now, for each address, you see these numbers here. These numbers are in hex. So 00500293, that's in hex. 064000313, that's in hex. So why are there 8 hex characters here at each address for an instruction? Because each instruction is 32 bits, exactly. So see, this is just showing you the 32 bits for each instruction in hex, right? Instead of writing out 32 zeros and ones, this was put in hex to make it more condensed. But what we want you to do in this assignment is we want you to take each of those hex, you know, those instructions in hex and convert them to binary. So you see, that's what was done in this table here. See, here's address 0, and now here's the binary for 00500293. In fact, and remember how you go from hex to binary? How do you do that directly? groups of four, right? So you see here, there's a 3, see here, there's a binary 3, 4 grouping. Here, there's a 9, there's a 9. Okay, so in this example, going from hex to binary, we're gonna have you do that, we're gonna give you a different listing and have you do the same thing. In fact, the listing is right below here. Okay, this is the table we want you to convert. Okay, all right, now comes the real challenging part of it, or different anyway, something you haven't done before, because you've converted hex to binary before. But what you haven't done before, and this is where you're gonna start getting familiar with the instruction set, is that now, once you have the machine code for each of the instructions, we want you to find that instruction in the instruction manual and write what the assembly code is. Okay, so you see how this is the machine code for this assembly instruction. So that's where you have to go to the assembler manual that's on Canvas. Let me show you where it is. It's down below. Yeah, right here. See the RISC-V assembler manual? That's where you'll find the instructions. So each instruction, like here's the add instruction. Here's the 32 bits. Okay? Every instruction has 32 bits. Add I, like you look at them all. And there's like 60 instructions. So you're probably thinking there, wait a minute, this is gonna be really tedious, right? Because you're gonna have this long 32 bits and you gotta kind of match it, okay? Well, to make it a little bit easier for you, one of the things to note is that the last 7 bits of each instruction is called an opcode, okay? And we'll talk more about the significance of that later on. But for this assignment, that's where I would start if I were you, is look at the last 7 bits. See, these 7 bits here, bits 0 through 6, that's the opcode. And that should get you to, it should narrow down the number of instructions that it could be. Okay? Then once you have, you find the opcode, notice that like for this instruction here, this is add I think, this is add I. Yeah, this is add I. Okay, so yeah, here's the machine code. And then you see, here's the instruction, the actual assembly language instruction. See, here's the name of the instruction. RD stands for destination register. That's where the result of that operation is going to be put. RS1 is a source register. IMM stands for immediate. What did we say an immediate was in this class? A constant, just a number, okay? Now, RD, RF1, where do you think those registers are? In what module that we talked about today? That's in the reg file. Okay, all your source and destination registers, because again, every operation happens in the reg file. Okay, and how many registers are in the reg file again? 32. And how many address bits do we need to address 32 registers? 5. So look, this command has RD, RF1, and then when you look at the machine code, see right here, RD, 1, 2, 3, 4, 5, 5 bits. See, the reason why it's 5 bits is because the address of whatever register you're using to put the result in would go there. So let's say, once you convert those hexes into binary, and let's say there's a binary 10 here, that means your destination register is register 10. Okay, and same thing over here for a source register, RF1. See, there's 5 bits. So those 5 bits are the address of the source register you're using. And now here, immediate is 12 bits. Well, that's the number. Okay, and you see, oops, question?
What does RD stand for?
Destination register. So what's meant by destination here is that's where the result, after this adding is done, because if you read the description here, this instruction is just taking the number and adding it to whatever data, whatever number is in RF1, and then putting the result of that addition in RD. Yeah. Okay? So, again, one of the purposes of this assignment is to get you started in getting familiar with the instructions that are in the instruction set for this microprocessor. Okay, so it can be a little tedious, this assignment can be a little tedious, but it pays off dividends in the long run. Okay? So that's what you do first, is you generate a table. Oops. So you're gonna generate a table just like this one, but for the hex listing 2, the one below it. You're gonna generate that table with this hex listing right here. Okay? Does everybody got an idea what to do with that? All right, so that's the first part of this assignment. Okay, the next thing, once you do that, what I recommend is watch the video I have on Canvas, because again, it steps you through what you have to do after that. It shows you how to create a mem file. You're gonna see it's very simple, actually. It's only like 3 clicks. So you're gonna generate a mem file, and then it shows you how to input that mem file into Vivado, and it's just like putting a design source. So again, it's pretty easy. Also, I explained some of the code that's in the program file that we give you that Dr. Hummel designed. And I show you the code to simulate it. Okay, so I show you what you need for your sim file. Also, I show you the mem files at hex listing within Vivado, and I show you a successful simulation timing diagram. Right, so basically what I show you in the video is what you have to go through. And then what you submit for this assignment is you submit this table that you created, right, a hard copy of it. You also submit the mem file hex listing from Vivado. And again, I show you exactly what it is in the video. And then also you submit a hard copy of a successful simulation, the timing diagram. Okay? Because you'll see if you're successful, your timing diagram, it's gonna step through these addresses where the program is, and it's gonna show that you're outputting the right instruction. That the program is outputting the right instruction. Okay? All right, so that's all I had for a lecture today. So for the rest of the class, you can work on your assignments. Once we get to where you work on assignments, you don't have to stay in the class. I mean, if you want to go somewhere else and work on it, that's fine. If you decide to leave though, please, before you leave, make sure your name is up on the sideboard there. Does everybody know who they're going to be partnering with? I mean, if I have anyone that doesn't have a partner, I'll assign them, but let's see, do we have everybody here today? Let me just check real quick. I just want to make sure. Okay, no, Elliot's here, Kaylee's here. Leonardo's here. Is Timmy here? Did Timmy? Okay, Timmy's here. Aiden's here. Daniel's here. Chad's here. Audrey is here. Joseph is here. Leonard is here. Ava's here. Is Chris here? Chris Kwan? Oh, Chris? Oh, you look different. Maybe it's the glasses. Do you normally wear glasses? Oh, okay. I think that's what was throwing me off. Jacob's here. Christian's here. Did Chase? I don't think Chase is here, right? Chase didn't show up. Okay, Chase is not here. Thomas is here. Rodrigo's here. Mark is here. Alexander's here. Ivan's here. Euclid's here. Hunter's here. Jack is here. Evan's here. Avery's here. Michael's here. Niall is here. Santiago. So just Chase isn't here. Does anyone know Chase? Do you know if he's staying in the class? Oh, okay. All right. All right. So anyway, like I said, the rest of the time is yours, but please, before you leave, make sure your name is up there.
So like, So like earlier, the art one that says five is the address.
Yeah. Yeah, and same for RD. That, like, when you look, you'll see that whenever there's a child. Five. Red dogs.
I think about it, my God.
Red dot, okay. And, you know, your source and your definition and, instruction. It's always a red dot, red dot. Yeah, what does it say? I think- Yeah.
That's not there.
Oh, we have to.
Well, you can see the cloud. Yeah, I just thought you was here. That's okay.
Okay, I know.
Maybe part of that. Oh. I didn't. I just wonder if I actually have a green.
This was not like the last 7 days.
Well, let me look and I'll get back to you. And I'll get back to you. So. I'm gonna let. I can give you. The best thing is, yeah, I could do it right here. Hold on just a second. Could you- Yeah.
But I.
Say that again?
So I did get a video for Yo sent me it, but I.
I can give you access. Okay. Just need your Cal Poly. Copy it. HCS, like, SC. Yeah. All right, so you know, it sends you like an, yeah, see, so it's just pending you. You can be all that. And then. Like. That'll tell him the same thing. Eric, later today at some point, just send me an email to remind me to send you permission. Okay. Okay.
I was in.
Yeah.
This one.
Well, this here, you down like here, that's just, that's the log now. No, I can show Canvas, you can just download it, and you can. Just can a log file. Yeah, see right here. So yeah, that file has that. Yeah, that's what student.
And then this. So this.
Well, no, this is. Is there a difference? Yeah, really? Let me see. Yeah.
One.
Yeah, yeah, let's see. Oh, so what is that? So. So. It's. I never noticed that before. Hold on. You might have brought something up that is important, so let me check what I have. Let's see. Had it somewhere. Like, put it. I think it's over there. Okay. Yes.
Well, yeah. We're sorry, let's look at the program. And I would like,
This one is within, this is on Canvas. Why doesn't it match what I did? Yeah.
it looks like this is just part of the.
Is this under the median? But like, show me when you got there again. Okay, so this is the actual.
Then this is not noticed. Because the example one should also. Awesome, I believe that this allows.
So go back there again. I'm puzzled, I don't know that. So. I got this from my. And if I go to. If I go, where I have meetings, because that's where you went.
You get one here, and then that whole.
That's it. Well, I'm just thinking that. It's like 7 instruments.
Yeah.
I don't really think that, I mean, I'll just have to do anything, that's all. Yeah, I think if I try to change it, I'm confused everybody. Let me think another minute. Yeah, let's just do the one. Yeah, it's just, but I'm glad you cleaned out. I never noticed this, but I don't know if maybe the manual got changed, because the last time I had this. So maybe the manual got changed. Yeah, but, yeah, just let's do the one in G, but I'll just have to. But thanks for pointing it out. I believe it's not perfect. For something. Yeah. Like the floating around, like yeah.
That's right. It's like alter or something. There's no. I don't know. It's totally.
Well, I see random formatting.
There, I
Here it is. It's something like this, would that be okay? I think the scale. Screenshot.
Yeah, exactly. in our. Yeah. Yeah, so just need to make sure that we're using that taking it.
Okay. I was gonna.
You're on there.
Nobody's gonna cover. So, using a. Thirty. You want it. One, where I get ahead of you, is how you differentiate between reg file location. Memory module location.
Well, if you look at the diagram. Yeah, we want to get into this. See that address for the memory module. That address for the reg file being the tree, it's going to be ultimate. Because what's kind of like this memory, it gets split up where these 5 bits are turned into, even that speeds 5 bits to turn into those.
There's a way to do it. You're never gonna be able to. Both. Maybe.
Like the next thing we talk about is we talk about this year. This regarding you'll see that its purpose is to give the memory module that has the first instruction is any program outside of the computer. And then like we talked about, it has instructions of word, right? It's all instruction are separated. So you see, that's why there's this +4 here. After, every time the program grain gets updated, it increments by 4. Yeah, and then you'll see that coming out of the memory, we get to this later, but coming out of the memory module, that's what's gonna determine the addresses for like your source registers and also your destination. So like address 1 is for address 1, address 2 is for address 2, WA is for the destination. Yeah, we get into more detail. Yeah.
Just a for.
Right. Right, exactly, yeah, the assembly line instruction uses the X. And then even later, you'll see that instead of using like X5 and 6, there's alternatively. That can be a more than it actually. But we don't get that until later, but it's part of the hardware. So that's why when you look at the instruction, and if an instruction has like an RD, RS, R2, you see within the machine code, there's the 5 bits, that's the address of those registers. So in your assembly language, you'll put like X5, but in the machine code, there'll be a binary 5 there. Because that's the address, and it's like, yeah.
I guess what one. The storage. Instruction. Somehow take the original.
What your question is getting is that this memory level is, get to later. Yeah, in fact, and at some point in this class, not for a few more weeks, but we'll get to a point where for every instruction, we're going to show you. So you'll see for certain instruction, data frame, certain other instructions. So like for flow instruction or slow instruction, the data has a lot different instructions. If you wanted to like, that. Low store don't involve the rich process. In fact, if you look here,
But I mean,
because if you look at, the different load instructions. Like let's see. I go like LB. So let's see, it's 3 bits actually. Oh, no, it's 12 and 13. So let's see. Let's see, for load byte, those 3, maybe this should be 3 bits instead of 2 bits. Oh, no, sign is 14. I see. Okay, so yeah, if you just look at 12 and 13 for byte, it's 0, 0. But if you look at it's 0, 1, and you see for LBU unsigned, it's 0, 0 with a 1 for the sign, but for when it's signed, see, it's all 0. So that's telling it whether it's unsigned or signed. This is telling it whether it's a byte or a word. Right. So you see, that's the other part of the memory module that's determined. Yeah. Now, good news is the memory module, just like the program, that you're given, that's, that's beyond what's expected in stuff. But these other modules you actually build in Bravado. Like the first one you build is, next class we'll talk about the program counter, and that's what you build the first one. All right. So good questions. Waiting. Right.
comment on like what? Like, what?
That's in one. Okay. Which is this first. What's that? Yeah, well, like you said, it's inverting in 91. I'm just wondering, maybe that's a mistake. Let me.
Like,
Oh, no, you're in your meeting room. This is a different.
Right. Actually, somebody pointed out. So. It's this one?
Oh, no problem. So let's do this one because this is already done.
Okay.
And
Now
now
let me look this, so this is JAL.
oh, yeah.
you look for this.
Well, let me just look at mine. So. Let's see, how many bits is that? It's 20 bits. So it's 20 bits, so. That's me. One, 4 1 1 1 it's 4 8 and then it's eight. Yeah, right away, I see. You can't just do anything. Is it 20? Hmm. Hmm. Yeah, I see the reason why, uh, this is new is because I actually have the one that's actually on Canvas. Let's see. See, this is the one I actually did,
Oh, okay.
but I'll just have to work through it. I haven't worked through this one yet. I'll just have to work through and verify, but it looks like it's not right.
Okay, so
What did you get for a number?
I
It
didn't know,
would be what? It'd be,
I didn't know how to group them, that's why it's kind of weird. Cause then what, so do I kind of follow the powers of twos, first like one and then go on to the X?
Well, however you do it, however it represents, it's the same number, just in different form. I mean, it looks like, let's see, 1, 2, 4, 8, 16, this is 30, 64, 128, it's like a big number.
Huge number. And it's 20 bits.
And it wouldn't be negative either. Right, because this would be your sign bit. Yeah, I'll have to sit down, like I said, I didn't do this one because I have these new ones, so I'll have to go through it just to verify, but it does look like it's not.
And wasn't partly to make sure, was because when I use this instruction, I wanted to make sure. I guess because I'm trying to understand what it's worded, like, what is negative 20 actually look? For. It is too much into the details, but.
Well, the other thing I'm trying to remember here. See, you see within the block here, see how it has immediate, then it has 20, 10 to 1, 11, 19. I'm
Yeah.
trying to remember that with these instructions. Maybe. Yeah, let me sit down and look at it.
Okay.
I think there's something to do with, like the particular instruction and how the bits are put together. It might have something to do with. the
Yeah, I
speed.
looked at it too like that, see what. I did. And I just don't know, like, you're right, like, what do I do with the first 12 to 19, and then 11, how are they unique?
Hold on a second. Let's see if, let's see, it says the 20th bit. Where would the 20th bit be? Would be,
It's a 20-bit long, oh, 20, okay.
oh, I think it's not, yeah, I think it's coming up with 20th bit. Did you have a question? Perfect. Mhm. 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 Right, yeah.
Yeah, that's good. Once we. Then, just go to me.
Well, these inputs are in text. You know, I mean, you're doing the right thing. I've taken that wall. So, this could get, so you can get. We had a piece of paper.
Oh, the levels are. So I would.
Mm. So you're starting with this, and you wanna show that it's plugging in. Okay. So yeah, this can go. This is just nice. Okay, so. Yeah, so if we add near. So this will be. So it should show, that this would be a day. This would be a there. Yeah, the E doesn't. Well,
So I.
oh, you need it. Well, remember, okay, let's back out. It's good, we one, that's how it's. Don't change this.
Oh, you gotta do these software.
Well, when looking at the the software, you're able to.
Yeah.
Wait, the other thing. The point there. Put it like. But, I mean, if you enter. So if you're probably working, you're able to take it down, it's. Right. So, here, take them out. Here. So the calculator. I think the only issue is that for some reason you're getting easier.
You have it.
Well, this means after the program takes the six to the community. The six, or the ten, or the legal center. It should come out.
I think it was up here.
If you.
He's just a wire to be on, Scott.
That, I mean, just like we did. Because
Well, there.
you start somebody in, you put the bitch out one. Right.
Really good.
Yeah, I think. In your reasoning, you're helping with the code, not do. Okay, all right, yeah, the number. So whatever number you put there, and add it to add it to the data in that register,
Yes,
and then use that as.
so this is right here.
Well, let's see, are we talking about the same example or are we talking about something? What example? Where is it? Where'd you get it from?
Oh, from the main. What do you mean? This is a homework,
Was it the same one we were looking at before?
right above it, the one.
Okay, so if you look at the command, so that's an SW command? Okay. Let's look at that. SW.
I guess my question is, make it a hex or does it have to be a solid number? See, this is a solid. number.
Yeah, so 4, and it, see, that would be the immediate, and see, here's where the immediate is, it's,
5 to 11.
yeah, 5 to 11. Let's see, this is, oh, no, the immediate's here, I'm sorry, immediate's here, that's the 5. Wait a minute, they broke it up, I guess, I guess the first 5 bits are here, and then the next, 7 bits are here, they broke it up.
Okay, so
Yeah.
this is like in power, right? 2 to some power. This is power 1 through
Yeah.
4.
Yeah,
or
this
0
would,
through 4, and power 5 to 11.
well, you know, this first, would be like how many 1? You know,
Yeah.
so there was,
Yeah.
yeah,
So
but,
they move better.
yeah.
So when we get to, so
So
what,
it, so it, so what is, yours is 4, right? So all these would be 0, and then you have a 4 here.
Yeah.
Yeah,
okay,
yeah, it's tricky because it's split up. And yeah, we'll talk more about why that's so later.
a bit of a big, let me check.
Yeah. No, all the time, you know, we work with the, but then you just. Yeah. Yeah. Make sure that it puts on. Has anyone, is everybody staying up here? Everybody, we're gonna take a picture soon. I'm still, this assignment, right? And that. Let's see.
Yeah.
Well, it's just.
That was, I was trying to get that was 7 here. Yeah, that. Yeah, yeah. But it's not, yeah. Oh, yeah. 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 Oh, yeah.
That's the finding. Oh. Remember.
Yeah. Other, oh, yeah, all people. And. When you're with. Yeah. 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 No, that's what they did, didn't Yeah. 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 That's what it's. Yeah. Here. You have. Yeah. That'd be me. Very fine enough.
Right, yeah, just go, I think the order, if you look at the criteria, I think the order is flow charts and test cases, then code, but yeah, just, you can put it all in a Word file and then just make it a PDF and turn it in. Okay, yeah, it's on Canvas.
I know all. Yeah. No.
Yeah.
One last question.
Mm-hmm.
For the software. We both turn in individual or is it?
Help each other.
And in the hardware and homeworks. That's also preparing. Or that's all here's.
Yeah, if you look at the syllabus, it's to go to the syllabus, just to make sure we're not doing something that's not.
I get it.
Um.
That's really the already.
To the, I wasn't sure about that.
Yeah, so you see for the lab work, you know, whether it's hardware, because see, there's more hardware than software, that's why it's 24/16. Hardware, there's 6, we see 2-person groups. But yeah, you just submit one per week.
Okay, got it. Talk to.
Yeah, it's mostly pairs, I mean, later on, like something that'll allow up to 4 people because, yeah, there's gonna be a portion of the class where for every real instruction is like 36 of them. You need to get a category. So it's like 36, so if they can get the 4, that way.
Split it out.
Well, the other thing is, I mean, it sounds more than it really is because there's a lot of like. Instead of 36, I'm making. But still, 4 or 5 or something. That's why I don't know. We gotta do these.
Okay, well, thank you.
Yeah, we'll get back to it on. This is the second time. I know more than. I gotta, this is something you talked about later. It's not something that. Yeah, I just did it. Look at it. Because I remember this coming up before, and there's something screwy about. Like when you get to these different, you see if you come over here. See, eventually we're gonna talk more about this, but the instructions are all like in categories and types. And I remember there's something screwy with date here, but I can't remember what it is.
Yeah.
I gotta look at my notes. I don't have my notes. Yeah, there is something. I don't remember what it is.
Let's go, let's go. Move on to-
Yeah.
Yeah. I think, let's get it, all I need.
Right. Yeah, yeah, and especially like, the video, would follow the video.
Yeah, I did. So I knew what to do. I just gotta get that last instruction right. And that's it.
Okay, so yeah, I'll think of it. That probably tomorrow. No. It is.
And like I said, I'm gonna-
I'll get back. to you.
that's good. Thank you.
That would be.
Shut this down.